Okay, and now we're going to continue our discussion of determinants and actually talk about determinants this time. And we're going to start with a definition. Here it is. It's a little bit crazy, so take your time reading it. But here it is, the definition. Let A be a square n by n matrix where A sub ij is the entry in the ith row and jth column. We define the determinant of A by the following. DETA is determinant of A. That's, by the way, not the notation that Ch1.3 is using, but it's pretty standard. And that's equal to that sum. And we'll go over that in a little more detail in just a moment here. Where alpha ranges over all possible permutations on the set 1 through n. And notice that each term in the sum there has two important parts. One is a product of the entries. If you'll see, it's A sub alpha of 1, 1 times A sub alpha of 2, 2 times A sub alpha of 3, 3, so on and so forth. And the other part that's towards the left is a negative 1 that is to a power. And that power is the number of inversions in that permutation alpha. So if you recall from a previous video, we talked about how to figure out what the inversions are in a permutation. That's going to be important. So basically it's that sum where you're taking a sum over all the possible permutations on the set 1 through n. Okay? The determinant is often written like this, with straight line braces to distinguish it from a matrix. So it's often written like a matrix, but you use straight line braces, and that denotes that you're taking a determinant of that matrix. And actually, this is the notation that Ch1.3 uses. But that's also a pretty standard notation. Alright, note, the determinant is only defined for a matrix that is square. It will become clearer as we progress through our discussion of determinants why the determinant of a matrix that is not square is undefined. There is no determinant for a matrix that is not square. And I guess I'll give you a preview. The reason for that is that remember, the determinant is a sum that is taken over all permutations on set 1 through n. And in order for there to be a permutation on the set 1 through n, the permutation is a function that has to be 1 to 1. Well, I guess I'll just stop there. It'll become clear as we go on. Alright, so let's go with some examples. Let's take an example. Alright, let A be equal to the matrix with entries 1, 2, 3, and 4. We will calculate the determinant of A using the definition. Okay, here we go. And the first thing I would do is, because we're taking a sum over all permutations on the set 1 through 2, because it's a 2 by 2 matrix, I'll just make a table. And this is the best way to go. Okay, so I've listed the possible permutations on the set 1, 2, and the permutations are 1, 2, or 2, 1. That's it. You have those choices. That's it. And the number of inversions for the permutation 1, 2 is 0, because, well, look at the previous video and figure out how to do the inversions. That's how you do it. And the number of inversions for the permutation 2, 1 is 1. There's one inversion there. So that's what we got. Moving on. Okay, so starting with our definition. Determinant of A is equal to the sum over all possible permutations on the set consisting of the integers 1 and 2. Alright, that's the negative 1 to the power, which is the number of inversions, and then you've got that product there, where that product depends on what the permutation is. Okay, moving on. Alright, now I want you to take notice of the first term in our sum. That comes from the permutation 1, 2. Okay, and take note, the number of inversions that we've put there in the exponent is the number of inversions in the permutation 1, 2. And also the terms in that product, A11 and A22, that comes from the permutation, right? 1, 2. And likewise, the second term in that sum comes from the other permutation, 2, 1, where we have negative 1 to the power, which is, well, the exponent is the number of inversions in that permutation 2, 1, and then the terms in the product, A2, 1 and A1, 2, come from that permutation 2, 1. So we've just basically plugged in what we've done in this step is we've just plugged in values here. I plugged in numbers for the permutation. All right. And if you evaluate that, you'll get the following. And I want you to take a look where we got the stuff from. Okay, so that power was 0 there because the number of inversions in the permutation 1, 2 is 0. Observe our table. Okay. And the number of inversions in the second term in the sum, the n2, the number of inversions in the permutation 2, 1, that's 1. So we put 1 there. Okay, and going back to the first term in the permutation, A sub 1, 1 is 1 because that's the entry in the first row, first column of our matrix A. And A sub 2, 2 is 4 because that is the entry in the second row, second column of our matrix A. Alright, and A sub 2, 1, that's 3 because 3 is the entry in the second row, first column of our matrix. And A sub 1, 2, that's 2 because that's the entry in the first row, second column of our matrix A. That's how we get that. And that ends up being equal to 4 minus 6, which is equal to negative 2. So there's our determinant, negative 2. Okay, note that the determinant of this 2 by 2 matrix is just the difference of the products of the entries on the two diagonals of the matrix. In this case, if you take a look, watch. The 4, that's just the product of 1 and 4, which is along the diagonal going from the top to the bottom and from the left to the right. That's also known as the main diagonal. And then we get the 6 is the product of 3 and 2, which is along the other diagonal. So we subtract those two quantities to get negative 2. Okay? And in fact, in general, given any 2 by 2 matrix, A equal to that matrix, we just put it in kind of a general form, the determinant is given by A sub 1, 1 times A sub 2, 2 minus A sub 2, 1 times A sub 1, 2, where that is just the product, or the difference of the products of the entries on the diagonals. So it's this diagonal minus that diagonal. And that always works for a 2 by 2 matrix. Now, it gets more complicated when the matrix gets bigger. Alright, now, here's a problem. Calculate the determinant of B, where B is the matrix with entries 1, 2, 2, 4. Let's calculate that determinant. And go ahead and pause the video, see if you can do that. You can use the shortcut we just gave you, or you can evaluate it by the definition. That's probably a good exercise to do it that way as well. But pause it and do it, and then unpause it. Ready? Go. And you probably did the problem by now. So here's the solution. Since the determinant is a 2 by 2 matrix, since the determinant of a 2 by 2 matrix is just the difference of the products of the entries along the diagonals, then we must have the determinant equal to 4 minus 4, which is 0. That's good. Okay, let's move on to the next problem, problem number 2. And it states, calculate the determinant of C, where C is the matrix, a 3 by 3 matrix, with entries 1, 2, 3, 4, 5, 6, and 3, 3, 3. And notice that you can't use this shortcut that we previously used on this one, because it's not a 2 by 2 matrix. So, go ahead and pause the video and tackle that problem, and then unpause it. Ready, set, go. Now here's the solution. And I've just presented the whole solution. I'm not going to go step by step on this one. But this is how I calculated the determinant. So go ahead and pause the video, check your answer, see if you did it right. Here's my answer. This is what I got. I got a determinant of 0 on this. Okay? And wrapping it up here on this, I did want to note, like the shortcut for evaluating determinants of size 2 by 2, there is a similar shortcut, not the same, but a similar shortcut for evaluating determinants of size 3 by 3. This shortcut will not be discussed, however, as it is less useful than the shortcut for the determinants of size 2 by 2, and frankly, we're going to have other methods for calculating the determinant that'll work as well, as long as you know what you're doing. Okay, another note. Shiloh develops a method for determining the signs of the determinant the signs of the terms of the determinant by connecting entries of the matrix via a line and observing the slope of that line. This method will be avoided entirely, and subsequent theorems, the proofs of which would rely on this method, will rely on material developed in Chapter 0 videos on permutations. And it's not meant, I want to say it's not like an insult. It's not that the method that's developed in Child's book isn't great, because one of the great things about it is that if you just do it his way, you don't really have to go into this whole like permutations thing. But that's not how I was taught. That's not how I prefer to do it. It has some merit in that you can just dive right into determinants and start linear algebra without really having to do much, without really having to have as many prerequisites. But I prefer to understand the traditional definition of the determinant and just hold myself to a little bit higher standard. So that's why we did it. And that's the end of this section. In the next section, we'll go ahead and prove some properties of the determinant. So we'll see you next time. See you there.